All right, so in your notebook on page 49, if you're on the same page as me, you glued in your water cycle thing with the tab so that when you open the tab, you have this blank page. This is what I want you to write on. We're almost halfway through our notebook, which is good because we're about halfway through the year, so that's working out pretty good so far. Does anybody know how much of the earth is water? 75% ish. So 3/4 or 75%. I would. I mean, if you already know it, and you're like, I got that memorized, that's cool, but wouldn't hurt to write down. I titled my page Hydrosphere. So this is why, in our solar system we have nicknames for our planets. Which one do you think is the red planet? Mars. Because it's red. We are nicknamed the blue planet because Earth is very blue, and that blue comes from all the water we have. Water is pretty important when you think about it because not only is the Earth 3/4 water, that's almost the composition of the human body as well. We're mostly water. So on my page I wrote hydrosphere as a title and I put 75%, or you can put 3/4 of the Earth is H2O. And if y'all don't know what H2O is by now, come see me. One chance, turn off. Snapchat later. So out of the 3/4 of our Earth that is water, almost the entire body of water on the Earth is ocean water or salt water, which means 97% of the water on Earth we cannot drink. And that should tell you how much water there is on the Earth, because when you think about how much fresh water we have around us, and to know that really only 3% of our water on Earth is fresh water, that means we got a lot. So if 97%, we know math, 97% is ocean water or salt water, then only 3% is fresh water. Now, when I say 3% fresh water, that is not just how much water is in the lakes and rivers. Fresh water comes from a bunch of different sources, and most of it is not even in the liquid form. Now, I do not want you to write down the next part because I've got a better way for you to write it that's a little less confusing. So think about that 3%. Now, don't write this down. I've got a better way for you to write it down. I know where you were. So out of that 3% of fresh water, almost all of the fresh water on Earth is in the form of ice. So like glaciers. 3% of water is fresh water. Almost all of it is ice. Groundwater, which is water under the surface of the earth. Remember, we have that water that when it rains, you got infiltration and it goes in the ground. That groundwater makes up the next largest percent. That's only 0.4%, not even a whole percent of the earth's water is groundwater. Surface fresh water, which is like your lakes, your rivers, your streams, your reservoirs, that's only 0.05%. And then the last 0.05% is stuff in the air. So rain, water vapor, and stuff in the soil, something in between the surface and under the surface. Now the way I want you to write this, so this is what I have so far. Out of that 3% of Earth's water, fresh water, 69% of that is ice or frozen water, like glaciers or snow. 30% is groundwater. And only 1% is surface water. So that's our lakes, streams, and the atmosphere. So if somebody asks you, where is most of our fresh water on the Earth's surface, what are you going to tell them? I'm sorry, where's the most fresh water on Earth? Where can I find that at? In ice. Don't be surprised if that's a test question. That seems to pop up a lot on EOGs and benchmarks. Most of our fresh water is in the form of ice. It's frozen. The next highest percent is groundwater. Water we cannot see, it's under the earth. And then only 1% is water that we can see on the earth's surface. I wrote in pencil first because I kept changing my mind about what I wanted to write. Now, since I'm a person that likes to learn with the aid of pictures, I like pictures. Helps me learn a little bit better. I put this in a perspective of a pie chart. So in the hydrosphere, which is all the water on the earth, and I don't draw a perfect circle, so there you go. Most of it, 97%, is salt water. Only 3% is fresh water. You don't have to color it, but you know I like color, so there you go. Yes. Sometimes on tests they like to put blank graphs or charts, and they say, look at this representation of the Earth's water composition. Which one represents fresh water? So you gotta know how to read graphs and charts like that. All right, now talking about freshwater breakdown. So if you take that little slice, that little blue slice, and you turn it into a pie chart. Worst circle ever. Put my little dot in the middle. The largest chunk on there, which is 69%, almost 70% of fresh water in the form of frozen stuff like glaciers. The next biggest chunk, groundwater, and this itty bitty little 1% slice is surface water. I wouldn't be surprised to see a graph like this on the test and asking you which piece represents glaciers or which piece represents surface water. They probably won't ask you which one represents groundwater, but I wouldn't be surprised they ask you which one is surface water, which one is glaciers. Let's do pink. So basically, the water that we see, like High Rock Lake, is a very small chunk of a very small chunk of water on the Earth's surface. Out of all the water on the Earth, the stuff we see is the smallest of the smallest. After you have finished copying that down, I want you to turn to your chemical and physical properties, which is page 18 through 21 if you're on the same speed as I am. I want you to take a couple minutes to review that, and then we're going to do a game on the smart board about chemical and physical properties and changes. Take a few minutes to review that. So if you're not on the same page as me, physical properties and changes starts on page 18, ends on page 21. right, let's put away your notes, see what you know. All right, the idea of this is a sorting game. And in this game, what you're going to do is take one of these terms down here and you're going to put them either under chemical properties and changes or physical properties and changes. So either the knight side or the dragon side. So all you got to do is, I just gave you that one. Click and drag it. So I'm going to select people at random. Just come up to the board, do whichever one you want to do. That last one out down there says rotting and decomposition. All right. Brian, you, followed by Aaliyah, then Trinity. Is it not dragging very well? Try it now. Oh, come on. One of these little fuzzy thingies are messing with us. All right, one finger. What's your fingers? Okay, where you trying to take it? Over there. It doesn't like your finger. Da-da-da-da. Okay, next. All right, freezing is a physical property. Very good, Trinity. After Trinity, it's Seth, then Elijah, then Vichan. So pH is a chemical property because you have to change the substance in order to find out what its pH is. That one is confusing. Yes, burning. Disadvantage about going first, you get all the easy ones. Color, very good. After Vichan, it's Logan, then Brooklyn, then David. Good. All right, Logan. Try flat finger. There you go. All right, David. After David, it is Ayana, Arleth, and Brianna.
It's not that one.
There you go. Yep. The point in which it boils. You don't change what the stuff is when it boils, so it's physical change. All right, Ayana, Arleth, Brianna. Oh, you were dragging about 8 your night. Not like your finger. Do a flat finger. Take it to the treasure chest. It's treasure. There you go. Melting, anytime you have a change of state. All right, Arlen, you're up. Anytime you have a change of state happen, it's always physical. You're not changing what it is, you're just changing the state of matter. Very good. All right, Brianna, and after Brianna, it's Ruben, Deontay, and Kamaya. Decomposition is a chemical change when stuff rots. It's breaking down. Happy Dragon. All right, Deontay. Good. Kamaya. After that, it's Tyvon and Lourdes. Good. Good. All right, Lourdes. Flammability, how easily catches on fire. Very good. All right, don't think if you didn't go that you're not going to get a turn. These are all just changes. There's really no properties in this one. All right. First up, Autumn, Tyra, and Noah. Y'all got cold fingers. You got cold fingers.
I put it over there.
There you go. Take it up to a ship. There you go. Anytime you have something change color randomly, like we did that one experiment where it changed purple all of a sudden, that's a chemical change. Good. All right, after Noah, it's Brittany and Brian H.
Where's it? Oh.
All right, next up is Seth, Vichan, and David. Good. Good. After David, it's Ayana, Ruben, and Arleth.
Push up.
Good. All right, Ruben. Come on, Ruben.
Oh, dang.
Very good. After Arleth, it's Tyra, Logan, and Elijah. Logan, you're after Elijah. All right, then it's Brooklyn, Aaliyah, and Noah. And then Deontay. Brooklyn, Aaliyah, Noah, and Deontay. And I think that'll be everybody. There you go. All right, Aaliyah.
Right. You really do see.
Good, that's what we talked about yesterday. Look, she's like, oh, it was right, yay. That's just changing from a solid to a gas. Good, gas to a liquid. All right, take us home, Deontay. Ooh, why do y'all leave this for last? That's why. Y'all freak out about that word. Remember, a precipitate is a solid. So where there was no solid before, you've made a solid. So you mix two liquids, you get a solid. You mix a liquid and a gas, and you get a solid. That is a chemical change. You're creating something that wasn't there before. So when you see the word precipitate, not precipitation, but precipitate, think chemical change. All right, get out your review packets. Let's go over some answers. A lot of you, I see some scribble scrabble on your packets, which is exactly what I wanted, so good job.
Read is yours. You know what?
What I take it,
Just the way you write. All right. So the idea of this is that you are not supposed to just answer the questions. So if I'm walking around and I'm seeing that you're just answering the questions, that's an issue. You're supposed to use the strategies that we went over. Your packet should look messy. There should be drawings, there should be notes. This is how I want your scratch paper to look like whenever you turn in on benchmarks. I want to see stuff written on it. And not the cute little doodles that y'all did before. They're very cute, but that's after the test. I want you to make it messy before you turn the test in.
All right, we went over the first few, and for some reason you don't have your packet today, which is a bummer because you're supposed to bring it with you. Then you need to write down the answers somewhere so you can go back and mark them later. Remember the first one was element. We already went over the first few. Second one was A. Number 3. Exposure is horrible. There we go. Physical change is a change in states. That's A. Number 4. Homogeneous mixture has 2 or more substances blended evenly, while a heterogeneous mixture contains different materials that are unevenly distributed. That's C. I think that's as far as we got as far as discussion. Which best describes a compound? I think you guys have got this definition down pat because you know to look for what keyword now. Different. That's going to be the key right there that separates a compound and a molecule. They are very similar except for that one key word. So number 5 is B. Number 6, they give you a chemical formula. I know we've seen this question several times, or something like this. It tells you we have a reaction, it's in a closed container, so nothing can escape. So what's true about the equation shown below? You don't even need that equation. You should know that in the law of conservation of mass, the number of atoms and the mass of the reactants, which is the left side of the equation, equals the atoms and mass on the product side, which is the right side of the equation. They put that equation there to give you kind of a visual example, but honestly, you could just skip by it and just read the answers. You should know that the definition of conservation of mass means the products equal the reactants. The thing that's going to trip you guys up that you need to be careful about is this one right here. Molecules, the mass in molecules, molecules and atoms, because you see the word, okay, this equals that. Be careful because molecules are an arrangement of atoms. That's saying that if you have CO2 on one side, you gotta have CO2 on the other. Not necessarily. They can be rearranged. So saying that they have the same molecules, that's not true. All right, number 7. They put numbers in there making you think like it's a math equation. Kind of not. You don't need to do any math. All you need to know is that when you have 20 grams of vinegar and 5 grams of baking soda, how much should you have after the reaction if it's a closed container? 25. If it's a closed container and you have 20 grams of vinegar and 5 grams of baking soda, when you're done, your product should equal 25 grams. Law of conservation of mass. But they're saying that it only equals 16.3 grams. So something happened. Something got lost. And the reason for that is a gas was released. So you need to know, 1, that during a chemical reaction, if it's not a closed container, then you may lose some stuff. And 2, you need to know what happens when baking soda and vinegar are mixed together. And we did that in class. But if you do not know what happens when they mix together, come see me. I'll do it for you. All right, number 8, which best describes the splitting of water molecules into hydrogen and oxygen? Okay, so you have H2O, and you got to separate it into H and O. That's a chemical change. You can't just separate it physically. You can't chop it up. So you know it's got to be a chemical change, and those bonds are broken. You're not creating anything, you're breaking it down. So it is A. All right, number 9. It's a math problem. It's asking you what's most likely the mass of product in reaction A. And since we are assuming that it's in a closed container, all you gotta do is add. 10 plus 5 is 15. Number 10. Another law of conservation of mass, they give you a chemical formula. You don't even need to look at it. You should know number of atoms in each element of the reactions equals the number of atoms in each element in the products. Now, if you wanted to balance the equation just to make sure, wouldn't hurt you. Now, number 11, you do have to count the atoms. You do have to balance the equation. Because you should know, in A, you have 2 hydrogen atoms and 2 oxygen atoms. So whenever you look at H2O, that's 2 hydrogen atoms, only 1 oxygen atom. So that does not show the law of conservation of mass because it is not balanced. Only balanced equations show the conservation of mass. Everything's got to be equal. All right, numero 12. Judging by how y'all did on the board, most of you got a pretty good grasp of physical versus chemical changes. A few exceptions on there, some things that are a little tricky for you. But I think most of you know that when you burn something, it's a chemical change. Number 13, you need to be careful with because this is the 8P11. This is what y'all struggled with the most. This is atoms, elements, compounds, molecules. It's asking what the simplest substance is. What is the one that's at the most lowest point, the most broken down? Oil is a mixture. It's a compound. Salt, what's salt? NaCl, it's also a compound. Sulfur, I can find that on the periodic table, so that's a what? Element. Water is what? It's H2O, which is a what? Compound. So the simplest one of those is what you'll find in the periodic table, which is an element. All the other stuff is more than one element. All right, this one, another thing that some of you struggled with specifically is why the periodic table is arranged the way it is. You need to remember that in those vertical columns, those groups or families, they are together because they have similar chemical reactivities. So the reason why hydrogen is located in group 1, even though it's not a metal, is because it has similar chemical reactivity to all those metals. A lot of you, first time around, selected D, which is very close. But that's not why stuff was originally arranged the way it is. It was arranged because of its reactivity. Because remember, whenever Mendeleev put the periodic table together, he was like, he didn't know anything about protons. He didn't know anything about the nucleus. All he knew is, hydrogen reacts the same way as these other things do, so I should probably put them in the same group. All right, metalloids, another periodic table question. This is that group that's not a metal, it's not a non-metal, it's a little bit of both. So it's not conductive, it's not non-conductive, it's a little bit conductive, semiconductive. All right, 16. This one really tricked you guys up. We didn't talk much about exchange of electrons. Now, I'll be perfectly honest, I don't like this question at this level. I don't feel like it matches your standards. But I don't make the test, so that's, it is what it is. But just know, the reason why elements in group 1 and elements in group 17, those alkalines and those halogens, the reason why they like to play together, why they like to react so easily, is because they give each other electrons very easily. If you were in group 1, you only have one outer electron, and you want to give it away so you can be stable. If you're in group 17, all you're missing is one electron, and then you're stable. So you want to grab an electron. So they get along real well. Everybody likes to work together to be stable. All right, you will have a periodic table again for your test. And on there, greatest atomic number. Remember the atomic number is the big number at top in that box? Just look on the periodic table. Which one has the biggest number? Which element most likely has similar physical properties to potassium? Remember, if we have similar properties, we're in the same family. So you need to look for something in the same family. The only one in the same family as potassium is sodium. Rusting, is it a chemical change or physical change? Somebody should know this because you did it right on the board. It is chemical. So it's which property? Rusting has nothing to do with how dense or how easily pounded into sheets it is. It doesn't have to do with conductive it is. It's a chemical reaction. Rusting is a chemical reaction. All right, last one. I haven't highlighted these yet. All right, this one makes it seem like a really, like a word problem where you gotta do something, you gotta add or subtract or something. Not really. All you gotta do is think about the law of conservation of mass. If you combine 3 atoms of chlorine and 6 atoms of sodium in a chemical reaction, how many atoms of chlorine must there be in the product? There must be 3 because you gotta keep everything equal. All right, number 21. So you mix together 2 clear solutions. There's no temperature change. Temperature stays the same. But you know a chemical change has occurred. And it's asking what would prove that a chemical change has occurred. So an increase in mass in the new solution, is that even possible? To make more of something in a chemical reaction? Does that fit the law of conservation of mass? No. It's a lie. Don't look at it. A solid precipitate was produced. Is that a chemical reaction? We know that because we just talked about it. Anytime you see that word right there, not precipitation, but precipitate. When you see that word, it's a chemical reaction. So that's probably it. A decrease in the volume of the new solution, that doesn't prove anything. 2 distinct layers were observed. That doesn't prove anything. Things layer out all the time. So it's got to be B. All right, so 100 students. So pretend like the whole team performed the same experiment. Testing the law of conservation of mass. So say y'all did the vinegar and baking soda with a balloon on the bottle thing that we did in class. So, but you all had different results. Why would that be? Which one do you think it is? Flawed hypothesis, identical lab procedures, inaccurate measurement, or contamination? Inaccurate measurement, who agrees? Yeah, if I told you to put 50 mLs of baking soda and 100 mLs of vinegar, and y'all were like, doop-de-doo, whatever, y'all will all get different results if you just eyeballed it. Unless you were extremely accurate in your measuring, you would have different results. That is the number one reason for wonky results in experiments is human error. All right, which one of these is most chemically reactive? See what you remember. You say? Who agrees? They may have a different answer. Why not 18? Those are the noble gases, yeah. And what are the noble gases? What are they also called besides noble gases? Anybody remember? What about inert gases? Does that sound familiar? That means they're stable. They're the most stable of the whole bunch. They're the chillest elements on the whole periodic table. That got real confusing for a few of you on that test. A lot of you put 18. No, you're thinking 17. 17's pretty doggone reactive too. 18's chill. Don't mess with 18. They're cool. All right, last two. All right, we're looking for an example of a physical change. Which one's an example of a physical change? There's more confident people in here. Y'all know the answer. What is it? There you go. Y'all know these answers. You act like you don't, but you do. All right. Here's that 8P11 that trips you guys up. Which classification best fits the chemical Al2O3? And don't trip that classification word. Just what is Al2O3? Is it a compound? Is it an element? Is it a mixture? Or is it a molecule? Why is it a compound? Two or more different elements. That's the key. So it is a compound. Very good. All right, hold on to these. Remember which standards I told you you need to focus on. In general, everybody needs to focus on 8P11. But don't forget the others too. All right, for the next few minutes, we're going to be working on these itty bitty worksheets. This, if you finish in class, turn it in. Make sure your name's on it, front and back. If you do not finish it, bring it tomorrow finished. You have like 5 or 6 minutes left in class, and this is really short. You may be able to finish that in time. On one side, all you're doing is marking it as a physical property or chemical property. And on the other side, you're marking it as either an element, compound, solution, or heterogeneous mixture. Homogeneous or heterogeneous. So what is it? So what is sand? Silver. Is it a compound? Is it an element? Is it a homogeneous mixture? Work on this individually because y'all can't use partners during the test. So if you're struggling on something, you need to know it. Oh. Get it.
Oh, yeah.